Hi there, my name's Nihal, and I'm here to talk about my chosen research paper called Towards Crossing the Reality Gap with Evolved Plastic Neural Controllers. Now, this paper talks about a key issue in evolutionary robotics, and in our case, a drone system that the team is trying to work with. Now, the big problem here is in the transferring of controllers and in simulation, trying to bring that into reality. Now, UAVs or drones, they tend to be more prone to failures and breakage when they're actually tested out in the field, right after running simulations of it. And even with simulation models that have higher levels of accuracy, they still tend to fail in reality. Now, why this is happening ranges from hundreds of different factors. Example, actuator kinematics. Actuator kinematics, they're basically unknown external factors that pretty much limits the performance of robots due to their complex nature and the way they're built. Example, a robot dog. The robot dogs have joints that have physical constraints on them due to the nature of their build. And how the team has gone about solving this is by building up algorithms on an already identified model, which is obtained using a data-driven process called system identification from a real drone model, and then modeling that exact dynamics from them. Now that they have a control algorithm, the main issue that the team was trying to solve next was the loss of performance that occurs when transferring that well-designed model into a real platform, which obviously has tons of different unknown factors that can go about and ruin their tests. And what the team came up with next was a spiking neural network. This managed to solve the majority of their problems. Now, why the team chose SNNs rather than ANNs is because ANNs follows a computation cycle of multiply, accumulate, and activate, where you feed the neural network a weighted sum of inputs and an activation function, and it generates an output accordingly. That is, this sort of loosely based off an actual neuron. SNNs, on the other hand, is based more closely on the biological modeling of neurons and more closely resembles to how a real neuron works and fires off in our brain. SNNs transmit data in the form of discrete spikes, which seem to gel well with the system because it allows the team to have more control over the complex computations that result from the SNN model in a much faster way while consuming way lower power levels compared to its non-spiking counterparts. In order to help with the process of designing this, the team has developed the eSpin software, which has been completely coded in C++, as it stands for Evolving Spiking Neural Networks. For this system, the team has chosen to implement the two-dimensional Ishkevich model due to its capability of exhibiting richness and complexity in neuron firing behavior with only two differential equations. Firstly, the variables that we need to know here are the recovery variables, the synaptic current, and the membrane potential. Here, one of the most important things to note is when the spikes are fired off, which is whenever V exceeds the threshold of membrane potential, a spike will be fired and be in use for Earth's reset following equation 2. Now I'm going to show you a video here. This video perfectly explains the spiking when it meets the given threshold. So the red line there is our neural network, and the blue line is the intended angle that the drone has to fly. And as you can see, it's doing this beautifully. Now, when we put mathematically on a diagram, we can see that the membrane potential V accumulates until it meets that threshold here. Now, our neural network looks very similar to this. It's made up of three layers and it follows the neat topology. We have the input layer, which has the encoding neurons which converts information, the hidden layer, which has spiking neurons connected unidirectionally, and that makes sure the most recent inputs are preserved when run. And then we also have the final and output layer, which will activate the spiking. Now I hope you remember that I mentioned Hebbian plasticity previously, and the best way to describe Hebbian plasticity is in the form of two strangers that randomly seem to love playing games. And the minute they realize this, they shoot each other an arrow, and now their bond just grew stronger, and they've now become gamer friends. With every subsequent arrow, this bond only seems to grow and grow until they can now instinctively predict when they're shooting their arrows. The formal definition of Hebb's plasticity theory is when two interconnected neurons on either sides of a synapse are both switched on or fired or activated at the same time, then the synaptic weight, which is the strength or bond in our case between them, should increase. And when they get fired at different instances, then their strength or bond decreases. Now the mathematical formula is as follows. The important bit here is equation 6, the time difference between pre and postsynaptic firing timings. In eSpin, the team has introduced their own weight-based Hebbian model derived from the nearest neighbor STP implementation with two additional evolvable parameters, where Km is a magnitude of the amplitude of weight changes and Kc is a correlation term that determines the magnitude between pre- and postsynaptic firing activity. These two factors are one of the most important variables in this paper, as they are the two factors that have been set to be evolvable so that the best values can be automatically located. Now, as you can see in this graph, we can see we've got a steady Hebbian learning curve, and the bond is fairly consistent and strong between the pre- and postsynaptic firings. This is awesome, as you can get better results in performance. We've now reached the coolest part of this presentation. The researchers have chosen a commercial hexacopter, the Tarot 680 Pro, fitted with the Pixhawk 2 autopilot system. It's set up in different control blocks, starting with the attitude controller, which controls the orientation of the controller, the yaw controller, which controls the yaw, height controller, which controls height. All of these calculate the appropriate rotor speed commands using the linear mixing matrix. These lead into the control mixing block, which combines the commands into the forces and moments block, which then takes these commands and calculates the thrust and torque of each rotor based on the relative airflow through the blades. The thrust and torques are then fed into the hexacopter dynamics block, which is then fed into our model's output. To build a loose model that can resemble the heap dynamics of the hexacopter, the team has to basically model the relationship between vertical velocity Vz, collective thrust D, and the vertical acceleration Az. The identified models is as follows. It consists of a couple of different variables, Kt and Kv being the only configurable coefficients, and B is a bias that is also tunable to make sure that the linear function will be expanded at some point. Taking two of those curves, we get this graph here, and we're able to formulate the linear function displayed in this graph here into this. We can then finally get the same random thrust values and feed it into two different models for validation of functional similarity, and then we get this graph here. What we get in response is that the identified model is closely resembling the original. The team of researchers' next step is to begin developing their SNNs using the neat topology. And the goal here is to make an optimal model that's able to drive the drone model to follow a reference signal with minimal error in height during the course of its flight. Each simulation flight lasts for about 80 seconds and is updated every 0.02 seconds. And then finally, the testing is able to kick off, and of course, this is sped up using the team's eSpin software. Initial tests consisted of a network topology of 2, 4, 1, which is the input head and output layer neurons, along with an additional bias neuron that's introduced in the next slide here. Is basically a constraint problem due to the fact that the height of the UAV has to be bounded within a certain range in reality, and how the team goes about solving this is using the feasibility first principle to handle the constraints. How this works is we've got a solution space. We divide the solution space and we've got two disjoint regions called feasible and infeasible. And what we have here is we give a solution for feasible where E modulus En denotes the normalized absolute error between actual and reference position, and for infeasible solutions we have Ti, which is the steps that the hexacopter has to successfully take to stay in place in the bounded region, and Tt is the total number of steps the entire simulation has. A couple of comparisons are conducted between plastic and its non-plastic counterparts to test which performs better. The team conducted 10 test runs for analysis, and these are all recorded offline on MATLAB. What we see here is a fitness table for 10 test runs comparing plastic and non-plastic counterparts. And evolution is terminated after 12 generations, so the performance doesn't improve. And as you can see, 9 out of 10 test runs, plasticity, when enabled, they get an increase in fitness. Another comparison that's been done to confirm the plasticity's behavior is when plotting it against a normal graph. Notice the non-plastic counterpart overshooting here. To confirm that plasticity rules aren't just working in this chosen network, the team decides to test it out in 4 other networks using the same model, with all of them following a reference signal. And the results are just as interesting. You can see the overshooting here, 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 and here. Controllers are basically the same controllers used in cruise control and vaporizers and stuff. And as you can see, obviously S and N's are way better in this, as we have overshooting occurring here, here, and here. This brings us finally to the end of our presentation, and I thank you so much for listening to me.